Alright, hi everyone. So today we're going to kind of combine the last few lectures. We have a singular goal. We're going to prove the following theorem. So this is going to be 28.1 theorem. We're going to prove that an integral domain A is a discrete valuation ring, a DVR, if and only if it's a local Dedekind domain. So this is kind of the culmination of the last few lectures. And then we're later going to use this result together with the previous lectures to prove that ideals in Dedekind domains have unique factorization. Okay. So let's go ahead and start the proof of this. First, let's consider the case. We'll show that a DVR is a local Dedekind domain. First, suppose A is a DVR. Okay. Remember, there are three conditions for something to be a Dedekind domain. It has to be integrally closed, has to have the property that every prime ideal is also maximal, and it has to be Noetherian. Okay. So we saw in proposition 27.5 right, that this thing is necessarily a principal ideal domain with a unique prime ideal. Okay. Since it's a PID, it's necessarily Noetherian. Right, every ideal is finitely generated. So there's one of our boxes checked. Recall also that PIDs are also UFDs. And we saw at the very beginning of the section on integral elements, A is necessarily integrally closed. So we proved that UFDs are integrally closed. And finally, there's a unique prime ideal, which also happens to be the maximal ideal of A. So since A has a unique prime ideal, it is necessarily maximal. And so A is a Dedekind domain. And clearly it's local because it has a unique maximal ideal, which is also the unique prime ideal. Okay, so this direction is not bad. The other direction will require a significant amount more work. Okay, so now we're going to suppose A is a local Dedekind domain. Okay. Since A is a local Dedekind domain, every prime ideal is maximal. Every prime ideal is maximal. And since A is local, there's a unique maximal ideal. And hence a unique prime ideal. Okay. So recall from 27.5 that DVRs are exactly, so an integral domain is a DVR if and only if it's a principal ideal domain with a unique prime ideal. So it remains to show, so by 27.5, it remains to show A is a principal ideal domain. And this is kind of the hard part of this problem. Okay, so we're going to outline the following steps, and then we're going to work through them one by one. Okay, so the first step, basically we're going to show that the prime ideal is principal. So the first step, we're going to let C and A be a non-zero non-unit. So you probably have to assume something like A is not a field here. And we're going to let M be the A module, A mod C. Okay. We're going to choose, so using the Noetherianness of A, we'll be able to choose an M in M so that the annihilator of this element, which I'll define, is maximal amongst all annihilators. So it won't necessarily be an honest maximal ideal, but it will be maximal amongst the annihilators. Okay, and then we're going to show, once we define this, we'll show that this annihilator is actually the unique prime ideal. Okay, so this is the first step, is to recognize this prime ideal as the annihilator of some module, and then we're going to show this annihilator is principal. I should make this more clear. So there's a capital M and a lowercase m, and I'm kind of mixing up the two, so this should be a lowercase m. And this should also be a lowercase m down here. Okay. If M is going to be, so M is some element of here, we can represent this as B plus the ideal C. Then will show that the annihilator here, the annihilator of M, is necessarily this ideal generated by C over B. Okay. And finally, this too will show that the prime ideal is principal, and we're going to let pi be this guy. For a non-zero proper ideal. A contained in A, we'll consider the chain A. So this is going to be a chain of A modules contained in K, the field of fractions of A. And we're going to show that we're going to consider this chain, and we're going to consider the chain to show A equals the ideal generated by pi to the M for some M, at least one. Okay. Notice that step 3 clearly implies that A is a principal ideal domain. So the result follows from step 3. Okay, so these are the 3 steps that we're going to follow. Let's go ahead and get started with step 1. So we're going to choose any non-zero 9-unit C in A. And we're going to let M A on the ideal generated by C. So again, you probably need to assume maybe A is not a field. Or maybe since A is a Dedekind domain, it has a unique non-zero prime ideal. So A can't be a field. Regardless, the case when this is not possible is a triviality. Okay. So we're going to let M be A mod C. We're going to note, I guess we're going to consider for M in M, we're going to consider something called the annihilator of M. These are just all the things that kill M. The collection of all A in A such that A times M equals 0. Turns out this is this annihilator of M, you can pretty easily check that this is an ideal, and we're going to call S. Note that S, this is the set of all annihilators of non-zero elements, such that set of all annihilators of non-zero elements. This is a collection of proper ideals of A. So no, it's proper because 1 is never in any annihilator. So yeah, it's a collection of proper ideals of A. Since A is Noetherian, I can find a maximal element with respect to inclusion in this set. So remember, we're assuming A is a Dedekind domain, which implies A is Noetherian. Find a maximal element of S with respect to inclusion. Okay. So we're going to call this element, I guess, yeah, choose m not equals 0 such that annihilator of m is maximal in the above sense. So it's not, again, it's not an actual maximal ideal. I guess it will turn out that it is, but a priori we don't know this is maximal. We just know it's maximal in this set S. So since there's a unique prime ideal of A, it suffices to show the annihilator of M equals P, the unique prime ideal. It suffices to show this thing is prime. Okay. So to do this, we're going to suppose, let's say A1 times A2 is in the annihilator of M. And let's say, consider A1 times M. So what can we say here? Note, right, that A1 times M I guess the annihilator of A1, anything that annihilates M is also going to annihilate A1 times M. So this necessarily contains the annihilator of M. And so by maximality, of oh, I see. I have to be a little careful. So if A1 times M equals 0, right, then A1 is in the annihilator of M, and we're done. If A1 times N is not 0, then by maximality of annihilator of M and S, we actually have to have equality here. So what does that mean? Well, notice that A2, so since A1 times A2 annihilates M, A2 annihilates A1 times N. This equals 0. So A2 is necessarily an annihilator of A1 times M, which we just decided was the annihilator of M. Okay, So this proves that either A1 or A2 is in the annihilator of M. So we see that this is a prime ideal. So this proves step 1. Okay, so we've recognized our prime ideal is the annihilator of some element here. Now we're going to continue to step 2 to show that this prime ideal is principal. So we're going to let M, this is the same M from above. We can write it as B plus C. So first we're going to show that this element C over B is actually an element of A. And then we're going to show that P is equal to the ideal generated by this guy. So note that P, which is now I recognize as the annihilator of my ideal, since it annihilates M, P times B has to be in C. So this is just translating the definition of what it means to annihilate M in this module big M. Since P times B is contained in C, we have in the fraction field P times C over B is contained in A. So the argument here is going to be kind of complicated. We're going to show that C over B is basically integral over A, and then we're going to use integral closedness of A. So to show its integral, we're going to use basically Dedekind's criterion. Since P is an ideal in A, P times B over C is an ideal in A. Wait. This should be C over B. Yeah. Sorry, I've got this screwed up here. Should be C over B is an ideal. So you can just check this using the definition of what it means to be an ideal. And since A is Noetherian, this ideal is necessarily finitely generated. As an A module. So that's what it means to be finitely generated as an ideal. It's the same as being finitely generated as an A module. Okay. We're going to suppose, for the sake of contradiction, wait a minute. I guess the same goes for if I replace C over B by B over C. Wait. Oh, because I've got this all screwed up. Okay. Now see. This should have been B over C all along. Because this, basically I'm dividing by C in this containment. B over C, B over C, B over C. Okay. Suppose for the sake of contradiction now, so I know this is an A module, and I know it's contained in A. Let's suppose I knew it was actually contained in the prime ideal P. Okay, and what can I say here? Well, by Dedekind's, I'm screwing up here. So, really, I shouldn't be telling you that, well, it is true that this is finally generated as an A module. The important part is P is finally generated as an A module. So, this, what do I want to say? P is this finitely generated A module, this finitely generated A submodule of the fraction field. If B over C times P is contained in P, then Dedekind's criterion of integrality says that this is necessarily integral over A. So by Dedekind's criterion, integrality I see that B over C is necessarily integral over A. And so, right, if this thing is integral over A is integrally closed, so it actually lives in A. So why is this a contradiction? Well, this is a contradiction. This contradicts M being non-zero. Since, well, if this is an A, M, which is B plus C, is going to be C times B over C plus C, which equals 0 plus C. Because this is an element of A basically by the fact that this is contained here. And so C times this thing has to be basically C times B over C is an element of the ideal generated by C. That's what I'm trying to say. Okay, so we've got this contradiction, right? Thus, this ideal is not actually contained in P, so it has to be the entire ring A. This has to be the trivial ideal. P times P over C equals A. In particular, 1 is in this thing. Well, actually, I can actually, what did I say? In particular, 1 is in the ideal P times B over C. So C over B has to be in P. And what's more, this equation actually gives me that P is equal to just multiplying both sides by C over B. A times C over B, which equals the ideal generated by C over B. Okay, so this proves step 2. This one's probably the most confusing step. We used integral closedness here, and we probably also used Noetherian to show that P was a finitely generated A module. Yeah. Okay, so we showed P's principle. Finally, we're going to use this kind of interesting chain to show that every ideal has a power of every ideal is principal. Okay, so there's step 2. Finally, let's move on to step 3. So we're going to let pi be this thing, the generator for our prime ideal. Okay, we're going to let, I guess, yeah, so for a non-zero proper ideal, A contained in A, we're going to consider the chain A contained in A pi inverse. And remember, this is a chain of A modules contained in the field of fractions. Okay, so that's where all these inclusions are happening. So let's consider what happens if the chain stabilizes at some point. If the chain stabilizes, basically this cannot happen. Then what does this say? This says that A times pi to the negative r equals A times pi to the negative r minus 1 for some r. And so what can we do? Well, this means that right? Once the chain stabilizes, yeah, okay, never mind. I see what's going on. Let's say A is non-zero. Then A times pi to the negative r equals A prime times pi to the negative r minus 1. Basically, clearing denominators will give me that A times pi to the r plus 1 equals A prime times pi to the r. Okay. And then I can kind of group terms and factor. I guess this is an integral domain, and pi is definitely non-zero. So this is going to be A equals A prime times pi, or no, I got the pi on the wrong side, sorry. So I'm using the cancellative property here. A times pi equals A prime. What does this mean? Now what does this mean? This means that A prime is necessarily in B, which seems fine. But the contradiction should somehow come from so I know A is necessarily contained in P. If I think I need to be more clever in how I choose this A. So let's stop here and let's consider how to choose this A a little more carefully. Okay. So I think I need to choose A something like, so what do I want to say? Yeah, I guess maybe I need to be, so basically what I want to say is by essentially Nakayama's lemma, the intersection of all of these, there may be a faster way to do this, but this is just what I can come up with on the spot. The intersection over all these ideals is trivial. This is a Noetherian local ring, so we can use Nakayama's lemma. And so in particular, since A is non-zero, A is not contained in one of these. So choose n minimal with A not contained in not contained in this ideal generated by pi to the n. Okay, and we're going to let A be an element of this difference. A kick out pi to the n. Okay, now I know A times pi to the okay, A times pi to the r minus 1. This is necessarily equal to some a prime times pi to the minus r. Okay. Notice that, oh, okay. Once the chain stabilizes once, then it's going to stabilize forever. So yeah. Okay, I think I see how to do this. Now, since a pi to the negative r equals a pi to the negative r minus 1, well, you can just do this again and say that this is equal to a to the pi to the minus r minus 2, and so on. So this equality here implies this equality here, because, well, you can just like use basically associativity. Okay. So now, in particular, a pi to the minus r equals a pi to the minus r minus n. And now, so with this a here, a times pi to the minus r minus n is going to be equal to a prime times pi to the minus r, and this gives rise to the equation a pi to the n, or sorry, a equals a prime times pi to the n. Okay, so yeah, I kind of screwed up this proof a little bit, but I kind of salvaged it in the end. This is how you would prove this. You'd use Nakayama's lemma to prove that the intersection of all these things is 0. Probably use Noetherian-ness here. Yeah. Okay. So what I want to say, this is a contradiction. So what does this mean? This means that the chain never actually stabilizes. So since A is Noetherian, right, this can't actually be, this entire set of chains can't actually all be contained in A. Okay. Since A is Noetherian, because A satisfies an ascending chain condition, this chain cannot be contained in A. Okay, so we're going to choose the smallest n again. Such that a times pi to the negative n is contained in A, but a times pi to the negative n minus 1 is not contained in A. Note that pi inverse times p, this is actually just equal to A, so that if a times pi to the negative n were contained in P, then A times pi to the negative n minus 1 would be contained in A. So basically, if I'm contained in P, then I can always squeeze out an extra power of pi. And this is going to essentially give us the result. Thus, right, since this is the minimal one that's contained in A, I can't actually have this one contained in P. A pi to the negative n is not contained in P, and since this is an ideal, it has to be the unit ideal. Thus, A pi to the negative n equals A, and so A equals pi to the n. Okay, so there's this kind of another complicated argument. You look at this chain, you argue that it can never stabilize. There's probably a better argument than the one I gave down here, but you argue that it never stabilizes, and once you know that it never stabilizes, it can't be contained in A. The whole chain can't be contained in A. Once you choose this minimal one, that can't be contained in P, and so it has to actually, A times pi to the negative n has to actually be the entire ring A, which forces that A is this principal ideal. Okay, so I should say the details of this proof are not super important. The important part is that you know that local integral or local Dedekind domains are exactly DVRs, and so basically the moral is that local Dedekind domains have a very high level of structure, and we're going to use that to prove unique factorization of ideals in the next lecture.